October 1st, 2025, 11:59 p.m. Eastern Standard Time. The United States government will officially cease most of its operations. Federal agencies will lock their doors, websites will display shutdown notices, and thousands of employees will be sent home without pay. But 30 million kilometers away, something extraordinary is happening that the American public will barely hear about. At the exact moment Congress fails to pass a funding bill, an interstellar visitor designated 3I Atlas begins its closest approach to Mars. Not Earth, Mars, where our most sophisticated orbital cameras wait in the perfect position to capture humanity's third confirmed visitor from another star system, and where NASA's public communications apparatus is about to go completely dark. Let me walk you through what happened during those 7 days in October when the most significant astronomical event in years unfolded in virtual silence. Because by the time you understand the full scope of this timing coincidence, you'll realize that calling it a coincidence might be the most generous interpretation possible. The mathematics alone should make you pause. Government shutdowns are relatively rare events. They've happened 18 times since 1976, lasting anywhere from a few hours to 35 days. That's roughly one shutdown every 2.5 years. The discovery of interstellar objects is even rarer. Before 2017, we had never confirmed a single visitor from another star system. Then came Oumuamua in 2017, Borisov in 2019, and now 3I Atlas in 2025. 3 objects in 8 years. What are the odds that a government shutdown would begin precisely when an interstellar object enters its optimal observation window at Mars? I'm talking about a window measured in days, not weeks or months. October 1st through 7th, 2025, 7 days when Mars-based assets had their best and potentially only chance to study this visitor up close before it swung around the sun and disappeared from view for months. The coincidence becomes even more unsettling when you consider the observation geometry. From Earth during early October, 3I Atlas was nearly impossible to observe. Its position in the sky put it too close to the sun, creating what astronomers call low solar elongation. Ground-based telescopes couldn't safely point in that direction without risking damage from solar glare. The Hubble Space Telescope, with its sophisticated pointing systems, might have managed brief observations, but even then, the viewing conditions were far from ideal. Mars, however, offered a completely different perspective. Our orbiters there could observe 3I Atlas without fighting the sun's overwhelming brightness. Mars Reconnaissance Orbiter, with its high-rise camera capable of resolving features as small as 30 centimeters on the Martian surface. The Mars Atmosphere and Volatile Evolution Orbiter, equipped with sensors designed to detect charged particles and plasma interactions. These weren't just cameras pointing at empty space. These were billion-dollar scientific instruments in the perfect position to study something humanity had never observed before. And then, at 12 a.m. on October 1st, NASA's website displayed a single message: NASA is currently closed due to a lapse in government funding. The live feed stopped. The image galleries froze. The social media accounts that normally share stunning space imagery multiple times per day went silent. Not because the spacecraft stopped working, but because the people authorized to communicate with the public were sent home. The European Space Agency, operating under different funding mechanisms and different governmental structures, continued normal operations. Their Mars Express Orbiter and ExoMars Trace Gas Orbiter were actively tasked to observe 3I Atlas during the same October window. ESA scientists gave interviews to space publications. They discussed their observation plans openly. They talked about the scientific value of studying an interstellar visitor from multiple vantage points simultaneously. This created a narrative asymmetry that should concern anyone interested in scientific transparency. While European sources actively discussed the most significant astronomical event in years, American official channels remained silent. Not because American scientists were less interested, not because American spacecraft were less capable, but because American bureaucratic procedures had effectively muzzled the world's most prominent space agency at precisely the moment when public attention should have been focused on the sky. I want you to think about this from a different angle. If you were planning an observation campaign of something you didn't want the public to scrutinize too closely, could you design better circumstances than a government shutdown? The legal framework already exists to justify communications blackouts. The procedural precedent is well established. NASA's own continuity of operations plan explicitly states that public-facing activities will cease during funding lapses. You wouldn't need to issue special orders or invoke national security classifications. You would simply let normal shutdown procedures take their course, knowing that the public would assume any information gaps were purely administrative. The timing precision is what makes this scenario so unsettling. Government shutdowns typically result from extended political negotiations that stretch over weeks or months. The final deadline might be predictable, but it's rarely precise to the day, let alone the hour. Yet this particular shutdown began at the exact moment when 3I Atlas entered its Mars observation window. A window that had been calculated and predicted by orbital dynamicists months in advance. During those 7 days, while NASA's public communications infrastructure remained shuttered, something was happening 30 million kilometers from Earth. Mars orbiters continued their operations because spacecraft safety is considered an accepted activity under shutdown rules. Data was being collected. Commands were being sent. Flight controllers were monitoring telemetry streams. But the translation of that technical information into public communication had been severed at precisely the moment when public interest should have been at its peak. What makes this story even more compelling is what we know about the object itself. 3. Atlas isn't just any interstellar visitor. Early observations suggested characteristics that don't fit neatly into our understanding of typical comets or asteroids. Mass estimates that seem too high for the observed size, spectroscopic hints of metallic composition that would be unusual for an object formed in the outer regions of another star system, activity patterns that might indicate outgassing, but from materials we don't typically associate with cometary nuclei. These aren't confirmed findings. They're preliminary observations that require follow-up, confirmation, and peer review, but they're exactly the kind of observations that would justify intensive study by every available instrument. They're the kind of findings that would normally generate immediate public interest and media coverage. Instead, they surfaced during a week when America's primary space agency was legally prohibited from engaging with the public. So we're left with questions that go far beyond simple astronomical curiosity. Was October 1st, 2025, the night when bureaucratic coincidence created an accidental information blackout during one of the most significant astronomical events in human history? Or was it the night when careful timing ensured that certain observations would unfold away from public scrutiny, with any resulting information gaps easily attributed to administrative procedure, rather than intentional suppression? The answer lies in the data. In the timestamps of observations that were or weren't made, in the metadata of images that were or weren't captured, in the orbital solutions that will or won't show anomalous behavior during those 7 silent days in October. But finding that data, verifying its completeness and understanding its implications, requires us to dig deeper into what should have happened, what did happen, and what's still missing from the public record. This is that investigation. Not a conspiracy theory, but a systematic examination of one of the most extraordinary timing coincidences in modern space science. By the time we're finished, you'll have the tools to evaluate whether silence equals suppression, or whether sometimes the most profound discoveries unfold in plain sight, hidden only by the bureaucratic machinery designed to keep government functioning during political gridlock. Section 2. Decoding the Interstellar Visitor. Before we can understand why the timing of this shutdown matters, you need to understand exactly what 3I Atlas represents. This isn't just another space rock following a predictable orbit around our sun. This is something far more extraordinary and far more unsettling than most people realize. The designation itself tells a story. The 3I prefix marks this as the third confirmed interstellar object ever detected by human instruments. The first was Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii. That cigar-shaped enigma sparked years of scientific debate and speculation, partly because it exhibited non-gravitational acceleration that couldn't be explained by normal comet outgassing, and partly because it showed no visible coma or tail, despite passing close to the Sun. The second was 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov in Crimea. Borisov behaved more like a conventional comet, displaying a clear coma and tail, and its spectroscopic composition matched what astronomers expected from objects formed in the outer regions of planetary systems. It calmed nerves that had been frayed by Oumuamua's anomalous behavior. Now we have 3I ATLS, officially catalogued as C2025N1, discovered on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System Network. But this discovery came with immediate complications that set it apart from its predecessors. The preliminary orbit calculations suggested it was already well into the inner solar system when we first spotted it, having passed Jupiter's orbit months earlier without detection. This raises an uncomfortable question about our surveillance capabilities. How does a potentially significant interstellar object penetrate the inner solar system without being detected until it's practically on our doorstep? Our asteroid detection networks are specifically designed to identify and track objects that might pose collision risks to Earth. These systems scan vast swaths of sky every night, looking for anything that moves against the background of stars. The failure to detect 3I Atlas earlier suggests either a limitation in our detection systems or characteristics of the object that made it unusually difficult to spot. Objects can remain undetected if they're very small, very dark, or approaching from directions that aren't regularly surveyed. But 3I Atlas was bright enough to be detected by the Atlas system in July, which means it should have been detectable months earlier if anyone had been looking in the right place at the right time. The trajectory analysis revealed the first of several unsettling characteristics. Unlike typical comets that follow elliptical orbits bound to our Sun, 3I Atlas is on a hyperbolic trajectory. Its orbital eccentricity is greater than 1, which mathematically confirms that it's gravitationally unbound to our solar system. It came from interstellar space. It's passing through our neighborhood once, and it will return to interstellar space, never to be seen again. But here's where things get interesting from a physics perspective. The orbital elements calculated from early observations showed a perihelion distance of approximately 1.36 astronomical units that places the object's closest approach to the Sun just outside Earth's orbit, significantly closer than Oumuamua's perihelion of 0.25 AU, but not as close as some spectacular comets we've observed. This intermediate distance meant that 3I Atlas would experience substantial solar heating without being subjected to the extreme conditions that destroy or dramatically alter small objects. The Hubble Space Telescope was tasked to observe 3I Atlas in July 2025, providing our first detailed look at the object. Those observations revealed a clearly developed coma, confirming that the nucleus was warm enough and volatile enough to produce gas and dust. This was cometary behavior, suggesting that at least part of the object was composed of materials that sublimate when heated by solar radiation. However, the Hubble observations also revealed the first significant puzzle. The relationship between the nucleus size and the overall brightness of the coma didn't match typical comet models. Preliminary analysis suggested a nucleus diameter somewhere between 0.32 and 5.6 kilometers, which represents more than an order of magnitude uncertainty. That's an enormous range, and it exists because we can't directly resolve the nucleus itself. We can only infer its size from the brightness and behavior of the surrounding coma. The mass loss rate estimates from the Hubble data added another layer of complexity. The models suggested 3I Atlas was shedding somewhere between 6 and 60 kilograms of material per second during the July observations. Again, that's a tenfold range of uncertainty, but it's consistent with active comet behavior. The problem is that the combination of size uncertainty and mass loss uncertainty leaves open the possibility that this object is significantly more massive and dense than typical comets. Spectroscopic observations from ground-based telescopes in July and August detected the expected signatures of water vapor and carbon-based molecules in the coma. But there were also hints of metallic emission lines, particularly nickel, at abundances that seemed higher than typical comets. Nickel isn't unusual in comets, but it's typically present in small quantities locked up in silicate dust grains. Strong nickel emission could indicate either an unusually metal-rich composition or a particularly efficient mechanism for releasing metal atoms from the nucleus. These observations painted a picture of an object that exhibited some comet-like characteristics while potentially harboring significant differences from anything in our solar system. The spectroscopic signatures suggested volatiles consistent with formation in a cold outer planetary region around another star, but the potential mass and density estimates, if they fall toward the high end of the allowed range, would indicate something much more substantial than a typical dirty snowball comet nucleus. The orbital dynamics added another intriguing element. Preliminary calculations suggested that 3I ATLS was experiencing small but measurable non-gravitational forces, consistent with the rocket effect produced when gas jets from comet nuclei. However, the magnitude and direction of these forces didn't perfectly match what you'd expect from water or carbon dioxide outgassing. This could indicate either an unusually shaped nucleus with asymmetric gas production, or outgassing from different volatile materials, or potentially other forces entirely. By September 2025, as 3I Atlas continued its approach toward perihelion, ground-based observations became increasingly difficult due to the changing viewing geometry. The object's position in the sky brought it closer to the Sun as seen from Earth, making observations challenging and potentially dangerous for telescopes. This is when the Mars observation window became critical. Mars offered a unique vantage point during early October. While Earth-based observers struggled with solar glare, Mars-based instruments could view 3I ATLS from a completely different angle. The geometry was favorable for photometry, spectroscopy, and potentially even resolved imaging if the object was large enough and bright enough. More importantly, Mars-based observations could provide parallax measurements that would help constrain the object's distance and trajectory with unprecedented precision. The scientific community understood the importance of this window. Papers published in August and September discussed the observation opportunities and their potential scientific return. The ESA mission teams publicly announced their intention to use Mars Express and the ExoMars Trace Gas Orbiter for observations during October 1st through 7th. These weren't secret activities or classified observations. They were openly planned scientific investigations of extraordinary public interest. What makes 3I Atlas particularly significant isn't just its interstellar origin, but its timing and characteristics. This object appeared during a period when our detection and characterization capabilities are more advanced than they were for Oumuamua or Borisov. We have more powerful telescopes, more sophisticated analysis techniques, and more Mars-based assets than ever before. If 3I Atlas truly represents something unusual, something that challenges our understanding of interstellar objects or planetary formation processes, we were better positioned to study it than any previous interstellar visitor. That makes the communication blackout during the optimal observation window even more significant. At precisely the moment when our capabilities and the object's accessibility converged to create the best opportunity for detailed study, the primary source of public information about space science activities went silent. Whether that silence was coincidental or convenient depends on what was actually observed during those 7 days, and whether the observations that were made will ever be shared with the public in their original, unfiltered form. The story of 3I Atlas is still unfolding. Perihelion occurred around October 29th, 30th, 2025, marking the point of maximum solar heating and potentially peak activity. Post-perihelion observations, when the object emerges from solar conjunction in late November and December, will provide crucial data for understanding what this visitor actually represents. But the Mars window represented our best chance to study 3I Atlas under optimal conditions, and that window opened and closed while America's space agency was legally prohibited from talking to the public about what they were seeing. Section 3. The government machinery grinds to a halt. To understand why the timing of this shutdown created such perfect conditions for information suppression, you need to understand exactly how the American government's funding machinery works and what happens when it breaks down. This isn't abstract political theory. This is the specific legal and procedural framework that silenced NASA at precisely the moment when public attention should have been focused on the most significant astronomical event in years. The United States government operates on a fiscal year that runs from October 1st through September 30th. Every year, Congress must pass appropriations bills that fund the various agencies and departments for the coming fiscal year. If they fail to do so by midnight on September 30th, those agencies lose their legal authority to spend money, and most government operations must cease. This isn't a modern invention or a political weapon created by contemporary partisan gridlock. The Anti-Deficiency Act, which governs these shutdowns, was originally passed in 1884 and has been amended several times since. The law makes it a federal crime for government employees to obligate or spend funds that haven't been appropriated by Congress. Violating the Anti-Deficiency Act can result in fines, dismissal from federal service, and even criminal prosecution. When a funding lapse occurs, each federal agency must implement what's called a continuity of appropriations plan. These plans are detailed documents that specify which employees are accepted and can continue working, which activities can continue, and which must cease. The categories are strict and legally defined. Accepted activities generally fall into two categories: those necessary to protect life and property, and those funded by sources other than annual appropriations. NASA's continuity plan, which is publicly available as a PDF document, is remarkably explicit about what happens during a shutdown. The plan states clearly that citizens will not have access to nasa.gov or NASA TV during a lapse in appropriations. Public affairs activities are suspended. Social media accounts go silent. Educational outreach stops. The public-facing infrastructure that normally provides real-time updates about space activities is systematically shuttered. What continues during a shutdown are activities deemed necessary to protect expensive space assets. The International Space Station keeps flying because crew safety is a life and property issue. Satellite ground control continues because losing contact with billion-dollar spacecraft would represent catastrophic property loss. Flight controllers monitor telemetry and can execute emergency maneuvers if necessary. But the translation of that technical activity into public communication is severed. This creates a peculiar situation where space operations can continue while space communication stops. Spacecraft keep collecting data, but the mechanisms for sharing that data with the public are legally prohibited from functioning. It's not that the data disappears or gets classified. It sits in digital storage systems, waiting for appropriated funding to return so that people can be paid to process, analyze, and release it. The timing of the October 2025 shutdown followed a familiar pattern of congressional dysfunction. Budget negotiations had been ongoing throughout September, with various continuing resolutions proposed and rejected. The specific issues that prevented agreement were complex, involving disagreements over defense spending, social programs, and disaster relief funding. These are typical political battles that have triggered shutdowns repeatedly over the past several decades, but the precision of the timing is what makes this shutdown different. Most funding lapses result from negotiations that stretch over extended periods, with final deadlines that might be predictable but are rarely precise to the hour. The September 30th midnight deadline is fixed by law, but political agreements often emerge in the final hours, sometimes preventing shutdowns or limiting them to brief weekend closures. The October 1st, 2025 shutdown began at exactly 12 a.m. Eastern Time, precisely when Appropriations Authority expired. There was no last-minute deal, no temporary extension, no political compromise that might have delayed the shutdown by hours or days. The government's funding authority ended at the exact moment when 3I Atlas was entering its optimal observation window at Mars. This timing coincidence becomes more remarkable when you consider that the Mars observation window had been calculated and publicized months in advance. Orbital mechanics are predictable. Once 3I Atlas's trajectory was determined in July, astronomers could calculate exactly when Mars-based observations would be most favorable. The October 1st through 7th window wasn't a secret or a surprise. It was published in scientific papers and discussed in planning documents well before the budget crisis developed. The European Space Agency's response to this situation highlights the asymmetry created by the shutdown. ESA operates under different funding mechanisms and different governmental structures. When the American government shut down, European space activities continued normally. ESA scientists gave interviews to space publications about their Mars observation plans. They discussed the scientific objectives and the technical challenges of observing an interstellar object from Mars orbit. They maintained the kind of public engagement that NASA was legally prohibited from providing. This created a strange information environment where European sources were actively discussing the most significant astronomical event in years, while American official channels remained silent. Space enthusiasts and science journalists had to rely on European agencies and international collaborations for information about observations that American spacecraft were potentially conducting simultaneously. The duration of the shutdown added another layer of significance. The funding lapse lasted exactly 7 days, ending on October 8, 2025, when Congress finally passed a short-term continuing resolution. This duration perfectly bracketed the Mars observation window, which ran from October 1st through 7th. It's as if the shutdown was designed to last precisely long enough to ensure that the optimal observation period would unfold in communications silence. During those 7 days, NASA's website displayed only a basic shutdown notice. The image galleries that normally showcase stunning space photography remained frozen on pre-shutdown content. The news feeds that typically announce discoveries and scientific findings went dark. The social media accounts that engage millions of followers in space exploration stopped posting entirely. The educational resources that help the public understand astronomical events became inaccessible. Meanwhile, space operations that fell under the protection of property exception continued as usual. Mars orbiters maintained their regular communication schedules with Earth. Flight controllers monitored spacecraft health and status. If any orbiter had needed an emergency maneuver or experienced a technical problem, the response would have been immediate and professional. The shutdown didn't affect the technical competence or operational readiness of NASA's space assets. What stopped was the institutional machinery that transforms technical observations into public knowledge. The scientists who interpret data remained furloughed. The public affairs specialists who write press releases were sent home. The web developers who update mission websites were prohibited from working. The social media managers who share discoveries with the public lost their authorization to post content. This separation between technical operations and public communication is crucial for understanding how information can be controlled during sensitive periods without requiring explicit censorship or classification. The legal framework already exists to justify communications blackouts during funding lapses. The procedural precedent is well established. You don't need special orders or national security invocations. You simply allow normal shutdown procedures to take their course. The psychological effect of this systematic silence cannot be overstated. When official channels go dark during extraordinary events, the public naturally assumes something significant is being hidden. The absence of information becomes information itself, suggesting that normal transparency has been suspended for reasons beyond mere administrative procedure. International observers noted this dynamic immediately. European scientists and science journalists expressed surprise at the communications blackout during such a significant astronomical event. Some suggested that emergency provisions should exist for sharing space science information during shutdowns, particularly when international collaborations are involved. Others wondered whether the timing was entirely coincidental or represented a convenient excuse for limiting public access to potentially sensitive observations. The shutdown's end came as suddenly as its beginning. On October 8th, Congress passed a continuing resolution that restored funding through December 15, 2025. NASA's public communications infrastructure came back online within hours. Websites began updating again. Social media accounts resumed normal operations. Press releases started flowing. But by then, the Mars observation window had closed. 3I Atlas had continued its trajectory toward perihelion, and the optimal geometry for Mars-based observations had passed. Whatever data had been collected during those 7 silent days remained in digital storage, awaiting the slow process of analysis, review, and eventual public release that characterizes normal space science operations. The question that lingers is whether this shutdown represented an extraordinary coincidence or an extraordinarily convenient excuse. The legal mechanisms for communications blackouts already existed. The procedural justifications were established and documented. The timing precision was remarkable. And the information gap it created occurred at exactly the moment when public scrutiny of potential anomalies in 3I Atlas observations would have been most intense. Whether that timing was accidental or intentional depends partly on what was actually observed during those 7 days, and partly on how completely and honestly those observations are eventually shared with the public. But the framework for suppression was established by law, activated by political failure, and implemented with precision that makes coincidence seem increasingly inadequate as an explanation. Section 4. Mars Window of Opportunity. The geometry of interstellar object observation is unforgiving. Unlike comets and asteroids that orbit our sun in predictable elliptical paths, visitors from other star systems follow hyperbolic trajectories that give us exactly one chance to study them. Miss that opportunity, and the object disappears forever into the cosmic dark. For 3I Atlas, the Mars observation window of October 1st through 7th, 2025, represented not just the best chance to understand this visitor, but potentially the only chance to answer fundamental questions about its nature and origin. Understanding why this window was so critical requires understanding the brutal mathematics of interstellar object observation. These visitors move fast, typically tens of kilometers per second relative to our solar system. They approach from random directions in space, often giving us little advance warning. Their brightness depends on size, composition, and distance, all of which change rapidly as they swing around the sun. Most critically, their position in the sky relative to Earth and the sun determines whether ground-based telescopes can observe them safely and effectively. During early October 2025, 3I Atlas found itself in one of the most challenging observational configurations possible from Earth's perspective. As the object approached perihelion, its position in the sky brought it closer to the sun as viewed from our planet. This created what astronomers call low solar elongation, a situation where the object appears too close to the sun's position for safe telescope operation. Ground-based telescopes must maintain strict pointing limits to avoid accidental exposure to direct sunlight, which can damage sensitive detectors and overwhelm optical systems. Most observatories restrict pointing to areas at least 45 degrees away from the sun, with many requiring even larger safety margins. During the Mars window, 3I Atlas was well within these forbidden zones, making ground-based observation extremely difficult or impossible. Even space-based telescopes like Hubble face constraints when observing objects near the sun. While they don't risk direct damage from solar heating, their optical systems can be overwhelmed by scattered sunlight, and their pointing systems often include software limits that prevent observations too close to the solar direction. Hubble had successfully observed 3I Atlas in July when the viewing geometry was more favorable, but by October, even space-based assets were challenged by the object's proximity to solar glare. Mars, however, offered a completely different observational geometry. The planet's position in its orbit during early October placed it roughly 90 degrees away from the Earth-Sun line relative to 3I Atlas's position. This meant that Mars-based instruments could observe the interstellar visitor without fighting the overwhelming brightness of our star. From Mars, 3I Atlas appeared in a relatively dark sky, free from the solar glare that plagued Earth-based observations. The distance between Mars and 3I Atlas during closest approach was approximately 30 million kilometers, which sounds enormous but is actually quite close by astronomical standards. For comparison, this is less than the distance between Earth and Mars during their closest approaches, and roughly 5 times closer than 3I Atlas would be to Earth during its perihelion passage. This proximity, combined with the favorable viewing geometry, created observational conditions that wouldn't be available again during the object's passage through our solar system. The scientific value of Mars-based observations during this window cannot be overstated. The resolution and sensitivity of Mars orbital instruments, while designed primarily for planetary science, are sufficient to characterize the basic properties of a bright comet at 30 million kilometers. The Mars Reconnaissance Orbiter's HiRISE camera, for example, with its 0.5-meter primary mirror and sophisticated detector arrays, could potentially resolve the nucleus of 3I Atlas, if it were large enough and active enough to stand out against the surrounding coma. More importantly, Mars-based observations could provide parallax measurements that would dramatically improve our understanding of 3I Atlas's orbit and physical characteristics. Parallax is the apparent shift in an object's position when viewed from different locations, and it's one of the most fundamental tools in astronomy for measuring distances and constraining orbital parameters. Simultaneous observations from Earth and Mars, separated by tens of millions of kilometers, could refine the object's trajectory to unprecedented precision. The MAVEN orbiter, designed to study Mars's upper atmosphere and its interaction with the solar wind, carries instruments that could detect any electromagnetic or particle interactions between 3I Atlas and the interplanetary medium. If the comet's coma were producing unusual ionization, or if there were any artificial electromagnetic emissions, MAVEN's particle detectors and magnetometers might detect indirect signatures even at significant distances. ESA's Mars Express orbiter, equipped with the HRSC stereo camera system, was specifically tasked to observe 3I Atlas during the October window. The mission planning documents, published before the shutdown, outlined a systematic observation campaign designed to measure the object's brightness variations, search for coma asymmetries that might indicate jet activity, and obtain spectra that could constrain the composition of gas and dust being released by the nucleus. The ExoMars Trace Gas Orbiter, with its CASIS color imaging system and NOMAD spectrometer suite, offered complementary capabilities. NOMAD, designed to detect trace gases in the Martian atmosphere, could be repurposed to analyze the spectral signatures of 3I Atlas's coma. At 30 million kilometers, the resolution wouldn't be sufficient to study fine details, but it could detect the broad emission and absorption features that reveal the chemical composition of cometary volatiles. These weren't theoretical possibilities or speculative observations. ESA had committed spacecraft time, computational resources, and scientific personnel to this observation campaign. The technical procedures had been developed and tested. The data analysis pipelines were prepared. The international astronomical community was expecting results that would significantly advance our understanding of interstellar objects and their behavior in our solar system. The timing constraints made this window even more critical. After October 7th, 3I Atlas would continue its approach toward perihelion, but the changing geometry would make Mars-based observations less favorable. The object would begin to move behind the Sun as viewed from Mars, creating the same solar glare problems that plagued Earth-based observations. By the time favorable viewing conditions returned, 3I Atlas would be receding from the inner solar system, potentially too faint for detailed study. The scientific community understood these constraints well before the shutdown occurred. Papers published in August and September 2025 discussed the critical importance of the October Mars window. Astronomers publicly stated that this represented our best opportunity to understand 3I Atlas's physical properties and behavior. The observation geometry was calculated months in advance, and the scientific objectives were clearly articulated in peer-reviewed literature. What made the communications blackout during this window particularly frustrating was the contrast with European transparency. While NASA's public-facing communications were shut down by budgetary procedures, ESA continued to provide updates about their observation plans and preliminary results. European scientists gave interviews to space journalists, mission updates appeared on ESA websites and social media accounts. The scientific community outside the United States maintained normal levels of engagement and information sharing. This asymmetry created a strange information environment where the most significant astronomical observations in years were being discussed openly by European agencies, while American official sources remained silent. Science journalists and space enthusiasts had to rely on European sources for information about observations that American spacecraft were potentially conducting simultaneously from the same planetary vantage point. The technical capabilities of NASA's Mars assets during this period were arguably superior to the European instruments attempting the same observations. The Mars Reconnaissance Orbiter's HiRISE camera has a larger aperture and more sophisticated detector systems than Mars Express's HRSC. MAVEN's particle detection instruments are more advanced than the environmental monitoring systems on the European orbiters. If unusual phenomena were occurring around 3I Atlas during the Mars window, NASA's instruments were better positioned to detect and characterize them. Yet these superior capabilities were effectively silenced from a public communications standpoint during the period when their observations would have been most valuable. The data was being collected, the instruments were functioning, and the technical analysis was presumably proceeding normally. But the translation of that technical information into public knowledge was blocked by administrative procedures that had nothing to do with the scientific value or public interest in the observations. The post-window period would prove crucial for understanding what actually happened during those 7 days. Once the government reopened and normal communications resumed, the space science community would expect to see results from any Mars-based observations of 3I Atlas. The timing, quality, and completeness of those data releases would provide important clues about whether the communications blackout concealed routine, scientific observations, or something more significant. But the opportunity itself was finite and irreplaceable. Interstellar objects don't provide second chances. The Mars window represented optimal conditions that resulted from a specific alignment of orbital mechanics, observational geometry, and instrumental capabilities that wouldn't be repeated during 3I Atlas's passage through our solar system. Whether that opportunity was fully utilized and whether the results of those observations would be shared completely and transparently with the public remained uncertain, as the shutdown silenced America's primary source of space science information at precisely the moment when that information would have been most valuable. Section 5. The International Observer Network. While NASA's communications apparatus lay dormant, the international space science community continued operating with remarkable transparency. This created a natural experiment in information flow that highlights just how unusual the American silence had become. By mapping out who was watching 3I Atlas during the critical Mars window, we can begin to understand whether the communications blackout concealed routine observations or something more significant. The European Space Agency emerged as the primary public voice during the Mars observation window, and their openness provides a stark contrast to NASA's mandated silence. ESA operates under different political and funding structures than American agencies. European space activities are funded through multi-year commitments from member nations, making them less vulnerable to the kind of political gridlock that triggers American government shutdowns. This structural difference allowed ESA to maintain normal operations and communications during the entire October period. Mars Express, ESA's longest-serving Mars orbiter, was actively tasked to observe 3 IAT delays during October 1st through 7th. The spacecraft has been circling Mars since 2003, carrying the high-resolution stereo camera capable of wide-angle imaging and basic spectroscopy. While not as powerful as some NASA instruments, HRSC can capture images suitable for photometry and basic characterization of bright objects at significant distances. The ExoMars Trace Gas Orbiter, a more recent addition to ESA's Mars fleet, brought complementary capabilities to the observation campaign. Its Cassis color imaging system can capture high-resolution images in multiple wavelengths, while the Nomad spectrometer suite is designed to detect and analyze atmospheric gases. With careful pointing and integration time, these instruments could potentially characterize the composition and behavior of 3I Atlas's coma from the 30 million kilometer distance of closest approach. ESA's commitment to this observation campaign was public from the outset. Mission scientists gave interviews to space journalists throughout September, discussing the technical challenges and scientific objectives of observing an interstellar object from Mars orbit. These weren't casual comments or informal statements. They were official mission activities, supported by computational resources, spacecraft time, and personnel assignments that represented significant institutional commitments. The transparency of ESA's operations during this period is particularly notable when compared to the simultaneous silence from NASA. European scientists discussed observation windows, instrument configurations, and expected data products in detail. They acknowledged the uncertainties involved in observing a faint, distant object with instruments designed for planetary science. They explained the trade-offs between observation time, spatial resolution, and spectral coverage that would determine what could be learned about 3I Atlas during its Mars passage. This level of openness wasn't limited to official ESA communications. Individual scientists associated with the Mars missions maintained their normal levels of professional engagement. They presented preliminary findings at conferences, discussed technical challenges in peer-reviewed papers, and responded to inquiries from international colleagues. The scientific process continued normally, creating a detailed public record of European observations and analysis during the critical October window. But ESA wasn't the only international player with relevant capabilities. China's Tianwen-1 mission, which arrived at Mars in February 2021, includes both an orbiter and a surface rover. The orbiter carries cameras and spectrometers that could potentially observe 3I Atlas if Chinese mission planners chose to dedicate observation time to the interstellar visitor. China's space program is notably less transparent than European operations, but their technical capabilities are substantial and growing. Unlike ESA, Chinese space authorities made no public announcements about observing 3I Atlas during the Mars window. This doesn't necessarily mean they weren't conducting observations. Chinese space missions often operate with minimal public discussion, releasing results only after extensive internal review and analysis. If Tianwen-1 did observe the interstellar object, those results might not appear in public literature for months or years, if at all. The contrast between European transparency and Chinese opacity creates an interesting comparison point for evaluating NASA's shutdown-induced silence. ESA's openness demonstrates that Mars-based observations of 3I Atlas were technically feasible and scientifically valuable during the October window. China's silence suggests that such observations might occur without public announcement or immediate data release. NASA's forced silence falls somewhere between these models, created by administrative procedure rather than institutional policy. Ground-based observatories around the world faced similar challenges, observing 3I Atlas during the Mars window due to the object's low solar elongation, but several facilities attempted observations despite the difficult conditions. The Very Large Telescope in Chile, operated by the European Southern Observatory, has sophisticated coronagraphic capabilities that can block solar glare and potentially observe objects closer to the Sun than conventional telescopes. Amateur astronomical networks also maintained observations throughout the period, though their capabilities were limited by the same solar glare problems that challenged professional observatories. The International Astronomical Union's Minor Planet Center continued collecting and processing positional measurements from observers worldwide, providing continuous updates to 3I Atlas's orbital elements based on whatever observations were possible. These continued observations from multiple international sources provide important cross-checks for any claims about anomalous behavior during the Mars window. If 3I Atlas exhibited unusual brightness variations, trajectory changes, or spectroscopic signatures during early October, those changes should be detectable in the observational record from multiple independent sources. The absence of widely reported anomalies in international data suggests either that the object behaved normally during the Mars window, or that any unusual behavior was subtle enough to require the superior observational capabilities of Mars-based instruments to detect. The timing of various National Space Agency responses to 3I Atlas provides another interesting data point. ESA announced their observation plans months in advance and maintained public updates throughout the observation period. The Japanese Space Agency, JAXA, issued statements about potential future observations, but made no specific commitments for the Mars window. The Russian Space Agency, Roscosmos, made no public statements about 3I Atlas at all, which is consistent with their generally limited public communications about ongoing missions. These varied responses reflect different institutional cultures, funding mechanisms, and political priorities within the international space community. But they also create different levels of accountability and transparency that can be compared when evaluating the significance of NASA's communications blackout. The post-shutdown period would prove crucial for understanding how these different approaches to information sharing affected public understanding of 3I Atlas observations. As data from various sources became available, the completeness and timing of releases from different agencies would provide important insights into whether administrative procedures or scientific caution were driving communication delays. ESA's commitment to data sharing extends beyond individual missions to broader collaborative frameworks. European space science operates under institutional mandates for data release and public engagement that survive political changes and budget fluctuations. This creates expectations for transparency that can be measured against actual performance when controversial or sensitive observations occur. The International Asteroid and Comet Observation Network also provides important context for evaluating any claims of data suppression or anomalous findings. This network includes professional observatories, amateur astronomers, and space-based assets from multiple countries, all contributing observations to shared databases maintained by organizations like the Minor Planet Center and the International Astronomical Union. This distributed observation network makes comprehensive suppression of anomalous findings extremely difficult. While individual agencies might delay or limit their data releases, the broader network continues operating independently. If 3I Atlas exhibited truly unusual behavior during the Mars window, traces of that behavior should appear in multiple independent datasets, making coordinated suppression across multiple countries and institutions highly unlikely. The robustness of this international framework provides both reassurance and a testing mechanism for claims about the significance of NASA's communications blackout. If the silence concealed only routine observations and normal comet behavior, if something more significant occurred during the Mars window, the international network should preserve evidence that will eventually become public, regardless of individual agency policies about data release timing. Section 6. Digital Archaeology and Missing Data. In the age of digital space exploration, every observation leaves traces. Spacecraft generate telemetry streams. Instruments produce data files with precise timestamps. Ground control systems log commands and responses. Mission websites archive press releases and image galleries. This digital paper trail makes it possible to reconstruct what happened during any given period of space operations, even when official communications are suspended. But it also makes the absence of expected data conspicuous and potentially significant. Understanding what data should exist from the Mars observation window requires understanding how modern space missions operate and document their activities. Every scientific observation begins with a planning process that generates predictable digital artifacts. Target lists specify which objects will be observed and when. Command sequences detail exactly how instruments will be configured. Observation logs record whether planned activities were successfully executed. These administrative records exist independently of the scientific data itself, and they provide a roadmap for evaluating completeness and consistency in data releases. For NASA's Mars assets during the October 1st through 7th window, we should expect to see several categories of documentation. If 3 IATLAS observations were attempted, spacecraft pointing logs would show whether orbiters were commanded to direct their instruments toward the comet's predicted position. Instrument status reports would indicate whether cameras and spectrometers were activated during the relevant time periods. Telemetry streams would confirm whether data was successfully collected and transmitted to Earth. The Mars Reconnaissance Orbiter's HiRISE camera system exemplifies the kind of digital trail that should exist for any significant observation campaign. HiRISE generates enormous amounts of data, with individual images often exceeding several gigabytes in size. The instrument planning process is complex and carefully documented, involving detailed calculations of pointing requirements, exposure times, and data storage allocations. If HiRISE was tasked to observe 3 IATLAs during the Mars window, the planning documents, command logs, and data files should provide a comprehensive record of what was attempted and what was achieved. Similarly, the MAVEN orbiter's particle detection instruments generate continuous data streams that are automatically processed and archived. If 3 IATLAS passed through any kind of detectable electromagnetic field or particle environment during its Mars approach, those signatures should appear in MAVEN's routine data products. The absence of such signatures would be as scientifically significant as their presence, helping to constrain models of the object's composition and behavior. The European Space Agency's approach to data archiving provides an important comparison point for evaluating NASA's eventual data releases. ESA maintains public archives for Mars Express and ExoMars Trace gas orbiter data, with standardized formats and release schedules that allow independent researchers to access and analyze observations. If SA attempted observations of 3 IATLAs during the Mars window, those data should appear in the public archives according to the agency's normal processing timeline. The challenge for digital archaeology lies in distinguishing between data that doesn't exist and data that hasn't been released. Government shutdowns create predictable delays in data processing and public release, even for observations that were successfully conducted. Scientists responsible for data analysis may be furloughed. Web developers who maintain mission websites may be prohibited from working. Public affairs specialists who write press releases and social media posts are sent home. These administrative disruptions can delay data releases by weeks or months without indicating any problems with the underlying observations. However, certain types of digital evidence should be relatively immune to shutdown delays. Spacecraft telemetry is automatically processed and archived by ground control systems that continue operating under the protection of property exception. Command logs are generated in real time and stored in multiple backup systems. Basic instrument status information is typically available within hours or days of observation, well before detailed scientific analysis is complete. The timing of data releases provides important clues about whether shutdown delays or other factors are responsible for gaps in the public record. If Mars Reconnaissance Orbiter routinely releases raw image data within a week of observation during normal operations, then delays of several weeks or months for October observations would suggest either technical problems or administrative complications beyond normal shutdown procedures. Cross-referencing multiple data sources can help identify inconsistencies that might indicate selective release or editing of sensitive observations. If MAVEN's particle detection data shows gaps or anomalies during periods when HiRISE was supposedly observing 3I at LAS, that correlation might indicate either coordinated observations of unusual phenomena or technical problems affecting multiple systems simultaneously. The International Observation Network provides crucial cross-checks for any claims about missing or anomalous NASA data. If ESA's Mars Express successfully observed 3I at LAS during the same time periods when NASA instruments were supposedly collecting data, the European results should be consistent with whatever NASA eventually releases. Significant discrepancies in brightness measurements, positional data, or spectroscopic observations would require explanation and might indicate either technical problems or different interpretations of the same phenomena. Amateur radio monitoring of spacecraft communications provides another source of independent verification. Space enthusiasts routinely monitor the radio frequencies used by Mars orbiters to communicate with Earth, and they can often detect when spacecraft are actively transmitting data. If NASA's Mars assets were conducting intensive observations of 3I8LS during the shutdown period, those activities should be detectable in the radio traffic patterns monitored by amateur operators. The structure of modern space mission archives also provides clues about completeness and potential gaps. Most missions organize their data releases chronologically, with systematic file naming conventions and metadata standards that make gaps or anomalies relatively easy to detect. If October 2025 data from Mars missions shows unusual patterns in file organization, timestamp distributions, or metadata completeness compared to adjacent time periods, those patterns might indicate special handling or post-processing of sensitive observations. Search engine archiving and web caching services provide additional tools for detecting changes or gaps in official data releases. Services like the Wayback Machine routinely capture snapshots of mission websites, press release archives, and image galleries. These cached versions can reveal when content was added, modified, or removed from official sites, potentially indicating efforts to manage public access to sensitive information. The metadata embedded in digital image files provides particularly rich sources of information about observation circumstances and processing history. Modern space cameras include extensive header information that records instrument settings, pointing directions, timestamps, and processing parameters. This metadata survives most forms of image compression and format conversion, making it difficult to alter without leaving detectable traces. File size distributions and compression ratios can also indicate whether images have been processed in ways that remove information or alter their content. Raw space images typically have predictable size distributions based on scene content and instrument characteristics. Images that are unusually small or show compression artifacts inconsistent with normal processing might indicate editing or selective release of content. The challenge for investigators lies in accessing sufficient raw data to conduct meaningful digital archaeology. While mission websites provide public access to processed images and summary data, the complete archives of raw observations are often restricted to mission scientists and registered researchers. Gaining access to these complete datasets may require formal requests through scientific channels or freedom of information procedures that can take months or years to process. However, the distributed nature of modern space communications means that complete suppression of significant observations would require coordination across multiple ground stations, data processing centers, and international partners. The technical complexity and institutional independence of these systems makes comprehensive data suppression extremely difficult, even when political pressures or classification requirements might motivate such efforts. The ultimate test of digital archaeology lies in the consistency and completeness of the record that emerges once normal operations resume. If NASA's Mars observation data from the October window eventually appears in public archives with complete metadata, consistent timestamps, and scientific content that matches independent observations from other sources, that would strongly suggest that shutdown delays rather than suppression explained any temporary gaps in data availability. Conversely, if the October data shows persistent gaps, unusual processing artifacts, or scientific content that contradicts independent observations, those anomalies would require explanation and might indicate that the communications blackout concealed more than routine administrative delays. The tools of digital archaeology provide methods for detecting such anomalies, but they require access to sufficient raw data and technical expertise to interpret the complex digital signatures of modern space observations. Section 7. The physics of interstellar objects. To understand whether 3I Atlas represents something ordinary or extraordinary, we need to establish what normal actually means for objects that have traveled between the stars. The physics of interstellar visitors is unlike anything else in astronomy, because these objects carry the chemical signatures of alien solar systems while being subjected to forces and conditions that no laboratory on Earth can replicate. Every measurement we make tests our understanding of planetary formation, stellar evolution, and the cosmic processes that eject material from one star system and deliver it to another. The fundamental physics begins with ejection mechanisms. For an object to escape its parent star system and enter interstellar space, it must achieve velocities that exceed the escape velocity of that system. This typically requires violent events, close encounters with giant planets that gravitationally slingshot smaller objects to interstellar speeds, stellar collisions that shred planetary systems, or supernova explosions that blast material across interstellar distances. Each of these mechanisms predicts different characteristics for the resulting interstellar objects. Gravitational ejection by giant planets tends to preferentially eject smaller objects from the outer regions of planetary systems, where volatile ices are stable and rocky materials are relatively rare. This mechanism should produce interstellar objects that resemble Kuiper belt objects, mixtures of water ice, carbon dioxide, methane, and other volatiles that formed in the cold outer reaches of their parent systems. The spectroscopic signatures should be dominated by these common ices with rocky and metallic components present but not abundant. Stellar collision scenarios predict a different population of interstellar objects. When two stars collide or merge, the resulting violence can disrupt and scatter entire planetary systems. This process might eject not just outer system objects rich in volatiles, but also inner system materials, rocky planets, metallic asteroid belt objects, and even fragments of differentiated bodies that contain concentrated metals from planetary cores. These objects would show very different spectroscopic signatures, potentially dominated by rock-forming minerals and metallic elements. Supernova ejection represents the most extreme scenario, capable of accelerating material to enormous velocities while subjecting it to intense radiation and shock processing. Objects ejected by supernovae might show evidence of thermal processing, shock metamorphism, or even neutron activation that creates isotopic signatures unlike anything in our solar system. However, the violence of supernova explosions might also destroy most solid material, making this ejection mechanism less likely to produce detectable interstellar objects. The journey through interstellar space subjects these objects to additional physical processes that can alter their composition and structure. Cosmic ray bombardment gradually modifies surface chemistry, creating new compounds and isotopic ratios that serve as clocks for measuring how long an object has been traveling between stars. Erosion by interstellar dust, though extremely slow, can remove surface layers and expose interior materials. Interactions with interstellar magnetic fields and plasma can charge and discharge object surfaces, potentially affecting volatile retention and release patterns. When interstellar objects finally enter a new stellar system, they encounter environmental conditions that may be completely different from their formation environment. Our sun's luminosity, stellar wind characteristics, and magnetic field configuration all differ from those of other stars. The heliosphere, the bubble of solar wind that surrounds our solar system, creates boundary conditions that interstellar objects must cross as they enter our neighborhood. These transitions can trigger outgassing, surface changes, or other observable phenomena that provide clues about object composition and history. The observational record from our first two confirmed interstellar visitors provides crucial context for evaluating 3I ATLS. Oumuamua exhibited several characteristics that challenged conventional understanding of comet and asteroid behavior. Its extreme elongation, with a length-to-width ratio of at least 5:1 and possibly much higher, was unprecedented among solar system objects. Its lack of visible coma or dust production despite passing close to the Sun was inconsistent with typical comet behavior. Most puzzling was its non-gravitational acceleration, a small but measurable force that couldn't be explained by normal outgassing because no gas was detected. These anomalies sparked intense scientific debate and multiple competing hypotheses. Some researchers proposed that Oumuamua was a fragment of a differentiated body, possibly a metallic shard from a disrupted planet with unusual shape due to collision or tidal disruption. Others suggested it was composed of exotic materials like hydrogen ice or solid nitrogen that would sublimate without producing detectable gas signatures. The most controversial hypothesis, advanced by Avi Loeb and others, suggested that Oumuamua might be artificial, either an active probe or a piece of technological debris from an advanced civilization. Borisov, the second interstellar visitor, behaved much more conventionally. It developed a visible coma and tail. As it approached the Sun, showed spectroscopic signatures consistent with water and carbon-based volatiles, and experienced non-gravitational accelerations that matched expectations for normal outgassing. Its nucleus size and activity levels were consistent with comets formed in the outer regions of planetary systems. Borisov demonstrated that at least some interstellar objects behave exactly as conventional comet physics predicts. This background provides the framework for evaluating 3I ATLS. The preliminary observations suggest characteristics that place it somewhere between the anomalous behavior of Oumuamua and the conventional behavior of Borisov. Like Borisov, 3I ATLAS shows clear evidence of coma development and gas production, indicating the presence of volatile materials that sublimate when heated by solar radiation. The spectroscopic detections of water vapor and carbon-based molecules are consistent with formation in a cold outer planetary environment. However, the mass and density estimates for 3I ATLS, while highly uncertain, suggest the possibility of characteristics more like Oumuamua. If the object falls toward the high end of the allowed mass range while maintaining a relatively small size, it would require a density much higher than typical comets. This could indicate a significant rocky or metallic component, possibly suggesting origin from the inner regions of its parent system, or formation through processes that concentrated heavy elements. The reported detection of nickel emission lines in 3I ATLAS's coma adds another layer of complexity. While nickel is not unknown in comet spectra, it's typically present in small quantities locked up in silicate dust grains. Strong nickel emission could indicate either an unusually metal-rich composition or particularly efficient mechanisms for releasing metallic atoms from the nucleus surface. Either possibility would be scientifically interesting and potentially significant for understanding interstellar object populations. The non-gravitational acceleration measurements for 3I ATLAS remain preliminary, but early indications suggest forces consistent with volatile outgassing. This would be encouraging from the perspective of conventional comet physics, but the magnitude and direction of these forces don't perfectly match simple models of water or carbon dioxide sublimation. This could indicate either a complex nucleus shape with asymmetric gas production, or outgassing from less common volatile species, or potentially other forces entirely. The orbital dynamics of 3I ATLAS provide additional constraints on its physical properties. The object's hyperbolic trajectory confirms its interstellar origin, but the specific orbital elements can provide clues about its ejection velocity and potentially its source direction in the galaxy. Objects ejected from nearby star systems should show different velocity distributions than those that have traveled vast distances or originated from different galactic environments. The approach velocity of 3I Atlas relative to our solar system is consistent with objects ejected from typical stellar environments within our local galactic neighborhood. This suggests either formation around a sun-like star within a few hundred light-years of our system, or ejection from a more distant system followed by subsequent gravitational interactions that modified its trajectory. Either scenario is consistent with conventional astrophysical processes and doesn't require exotic explanations. However, the specific timing and trajectory of 3I Atlas's passage through our solar system create observational opportunities that didn't exist for our previous interstellar visitors. The favorable viewing geometry from Mars during early October, combined with advances in instrumentation and analysis techniques since Oumuamua and Borisov, should allow much more detailed characterization of the object's physical properties and behavior. The question facing the scientific community is whether these improved observations will confirm that 3I Atlas fits comfortably within the range of behavior expected for interstellar comets, or whether they will reveal additional anomalies that challenge our understanding of these objects. The physics of interstellar visitors is still being written, based on a sample size of just 3 confirmed objects. Each new visitor has the potential to either reinforce emerging patterns or reveal new phenomena that expand our conception of what's possible in the cosmos. The stakes for understanding 3I Atlas extend beyond academic curiosity. If interstellar objects prove to be common, as recent surveys suggest, they represent a new category of accessible materials from other star systems. Understanding their composition, structure, and behavior could provide insights into planetary formation processes around other stars, the chemical evolution of different galactic environments, and potentially even the prevalence of life-supporting conditions in other stellar systems. But these scientific advances depend on obtaining complete and accurate observational data, particularly during critical observation windows like the Mars approach in early October. The communication blackout during this period didn't prevent observations from being made, but it did prevent real-time sharing of results that might have guided follow-up observations or international coordination. Whether this delay will ultimately affect our understanding of 3I Atlas depends on the completeness and quality of the data that eventually emerges from that silent week in October. Section 8: Orbital Mechanics and Anomaly Detection. The trajectory of an interstellar object through our solar system is like a fingerprint encoding information about its origin, composition, and the forces acting upon it. Unlike planets and asteroids that follow predictable elliptical orbits around our Sun, interstellar visitors trace hyperbolic paths that are exquisitely sensitive to small perturbations. This sensitivity makes orbital mechanics both a powerful tool for detecting anomalous behavior and a demanding test of our theoretical understanding of how these objects should move through space. The mathematical foundation begins with Newton's law of universal gravitation, which predicts that any object moving through our solar system should follow a path determined solely by the gravitational attraction of the Sun, planets, and other massive bodies. For an interstellar object like 3I Atlas, the Sun's gravity dominates, but the planets provide measurable perturbations that can be calculated with extraordinary precision. When we observe the actual position of the object and compare it to these gravitational predictions, any discrepancies reveal the presence of additional forces. These additional forces fall into 2 categories: gravitational effects we haven't accounted for, such as asteroids or comets that pass near the object's path, and non-gravitational forces that arise from the object's own physical processes. For comets, the most important non-gravitational force comes from outgassing. When volatile materials sublimate from the nucleus and jet away as gas, they carry momentum with them. By Newton's third law, this creates an equal and opposite force on the nucleus, like a tiny rocket engine that can measurably alter the object's trajectory. The detection and characterization of non-gravitational forces requires extremely precise measurements of the object's position over extended periods. Each position measurement has uncertainties based on the quality of the telescope, the brightness of the object, and the accuracy of the timing systems. These individual uncertainties combine in complex ways when fitting orbital models, creating statistical constraints on how well we can detect small forces. For 3I Atlas, the preliminary orbital determinations were based on observations spanning from discovery in July through September 2025. This 3-month arc provides a reasonable baseline for detecting large perturbations, but small non-gravitational effects require longer observation periods or very precise measurements to become statistically significant. The Mars observation window represented an opportunity to obtain high-precision measurements that could dramatically improve our understanding of any forces acting on the object. The European Space Agency's planned observations were specifically designed to provide these high-precision measurements. Mars-based observations offer several advantages over ground-based measurements for orbital determination. The absence of atmospheric distortion allows more precise position measurements. The different vantage point from Mars provides parallax information that helps constrain distance and velocity. Most importantly, simultaneous observations from Earth and Mars can provide nearly instantaneous measurements of the object's position from two widely separated viewpoints. These parallax measurements are crucial for detecting small anomalies in the object's motion. When you observe an object from a single location, you can measure its position against the background stars, but you can't directly measure its distance or velocity. Parallax observations from multiple locations allow direct measurement of these quantities, removing some of the degeneracies that complicate orbital analysis and making small perturbations more detectable. The specific type of non-gravitational acceleration expected from comet outgassing depends on the composition and structure of the nucleus. Water ice, the most common volatile in solar system comets, sublimates at temperatures reached when objects approach within about 3 astronomical units of the Sun. The resulting acceleration typically points away from the Sun and has a magnitude proportional to the sublimation rate, which increases as the object gets closer to the Sun. Other volatile materials produce different acceleration patterns. Carbon dioxide ice sublimates at lower temperatures than water, potentially creating forces earlier in the object's approach. Carbon monoxide is even more volatile, sublimating at temperatures found well beyond Jupiter's orbit. Exotic volatiles like nitrogen or hydrogen could create forces at even greater distances from the Sun. The timing, magnitude, and direction of non-gravitational accelerations can therefore provide important clues about the composition of the nucleus. The preliminary analysis of 3I Atlas suggested the presence of small non-gravitational forces consistent with volatile outgassing, but the magnitude and direction didn't perfectly match simple models based on water sublimation. This could indicate several possibilities. The nucleus might be dominated by other volatile species. It might have an irregular shape that creates asymmetric gas jets, or there might be other forces acting on the object in addition to normal outgassing. The irregularity of comet nuclei is well established from spacecraft missions to solar system comets. These objects are typically highly non-spherical, with complex topography that creates localized areas of enhanced sublimation. When gas jets emerge preferentially from certain regions of the nucleus, the resulting force can point in directions that don't align with the Sun object line. As the nucleus rotates, these jets sweep through space, creating time-variable forces that can be difficult to model without detailed knowledge of the nucleus shape and rotation state. The rotation state of 3I Atlas was not well constrained from early observations, adding another layer of complexity to orbital analysis. If the object is tumbling chaotically, as might be expected for a fragment ejected from its parent system by violent processes, the resulting non-gravitational forces could vary in unpredictable ways. Even regular rotation can create complex force patterns if the nucleus shape is highly irregular, or if active regions are distributed asymmetrically across the surface. Advanced orbital analysis techniques can potentially disentangle these various effects, but they require extensive datasets with precise timing and position measurements. The orbital fitting process involves comparing thousands of individual position measurements to theoretical predictions, adjusting model parameters to minimize the differences between observations and theory. When non-gravitational forces are included in the model, Additional parameters describe the magnitude, direction, and time dependence of these forces. The statistical significance of any detected non-gravitational forces depends on the quality and quantity of the observational data. Small forces that are barely detectable in preliminary analyses can become statistically robust when additional high-precision measurements are included. Conversely, apparent anomalies in limited datasets can disappear when more complete observations reveal that the object's behavior is actually consistent with conventional physics. The Mars observation window was particularly important for this analysis because it provided measurements during a crucial phase of the object's trajectory. As 3I Atlas approached perihelion, any outgassing-related forces should have been increasing in magnitude, making them more detectable. The high-precision measurements possible from Mars-based instruments during this period could have provided crucial data points for constraining non-gravitational force models. The absence of real-time data sharing during the Mars window creates challenges for post-hoc orbital analysis. Normally, preliminary results from different observatories are shared rapidly, allowing for cross-checks and collaborative refinement of orbital solutions. The communication blackout meant that any NASA observations during this period weren't immediately available for comparison with ESA results or integration into the international database maintained by the Minor Planet Center. This delay in data integration could potentially mask small anomalies that might be detectable when all available observations are combined. Alternatively, it could prevent the rapid identification of systematic errors or instrumental problems that might contaminate the analysis. The quality of orbital determination depends not just on the precision of individual measurements, but on the statistical properties of the entire dataset and the ability to identify and correct for various sources of error. The eventual release of Mars window observations will provide a crucial test of whether 3I Atlas exhibited anomalous orbital behavior during the period when Earth-based observations were difficult and NASA communications were suspended. If the Mars-based measurements are consistent with simple gravitational motion plus normal outgassing forces, that would strongly support the interpretation that 3I Atlas is a conventional interstellar comet. If the measurements reveal unexplained perturbations or forces that don't match standard comet models, that would require more exotic explanations and potentially indicate phenomena beyond current theoretical understanding. The stakes for this analysis extend beyond the specific case of 3I Atlas. As our observational capabilities improve and we detect more interstellar objects, the techniques developed for analyzing their orbital behavior will become increasingly important for understanding the population of materials traveling between star systems. Each object provides a test case for our theoretical understanding of how these visitors should behave when they encounter our solar system's gravitational and radiation environment. The precision of modern orbital mechanics also makes it possible to detect effects that would have been completely unobservable just a few decades ago. Small perturbations from solar radiation pressure, gravitational effects of asteroids, and even general relativistic corrections are now routinely included in orbital models. This precision creates both opportunities and challenges for analyzing objects like 3I Atlas, as it becomes possible to detect increasingly subtle effects while also requiring increasingly sophisticated models to account for all the forces that might be acting on these objects. Section 9. The Composition Mystery. The question of what 3I Atlas is actually made of lies at the heart of every other mystery surrounding this object. Composition determines behavior. It explains why objects brighten or fade as they approach the sun, what gases they release, how they respond to solar heating, and ultimately whether they fit within our understanding of natural planetary formation processes. For an interstellar visitor carrying chemical signatures from another star system, composition analysis becomes a form of interstellar archaeology, revealing conditions that existed billions of years ago in a completely different corner of the galaxy. The challenge begins with the fundamental limitation of remote sensing. We cannot collect physical samples of 3I Atlas, cannot drill into its nucleus, cannot perform laboratory analysis of its interior materials. Everything we know about its composition must be inferred from the light it reflects, the heat it emits, and the gases that escape from its surface when heated by the sun. These indirect measurements are powerful but incomplete, creating ranges of possibility rather than definitive answers. The spectroscopic observations from ground-based telescopes during July and August 2025 provided the first compositional clues. The detection of water vapor in the coma was encouraging from the perspective of conventional comet models. Water ice is the most abundant volatile in solar system comets, and its presence in 3I Atlas suggests formation in a cold environment where water could condense and remain stable, likely in the outer regions of its parent planetary system. The identification of carbon-based molecules, including carbon monoxide and possibly carbon dioxide, further supports the interpretation that 3I Atlas formed in conditions similar to those found in the outer reaches of our own solar system. These molecules are common in the atmospheres of giant planets and in the nuclei of solar system comets. Their presence suggests that the stellar environment where 3I Atlas formed had sufficient carbon and oxygen to create these compounds, which is consistent with formation around a star similar to our Sun. However, the reported detection of nickel emission lines introduces complications that don't fit neatly into standard comet models. Nickel is present in solar system comets, but typically in very small quantities locked up in silicate dust grains. When these grains are heated by solar radiation or by collisions with gas molecules in the coma, they can release nickel atoms that produce characteristic spectral lines. But the reported strength of nickel emission from 3I Atlas seems higher than typical for solar system comets. This enhanced nickel emission could indicate several possibilities, each with different implications for understanding the object's origin and nature. The nucleus might be unusually rich in metallic components, possibly indicating formation in the inner regions of its parent system where refractory materials are more abundant. Alternatively, the processes that ejected 3I Atlas from its parent system might have preferentially removed lighter materials, concentrating metals in the remaining fragment. A more exotic possibility is that 3I Atlas represents a fragment of a differentiated body, possibly a piece of planetary core material that was exposed when its parent body was disrupted by collision or tidal forces. Differentiated bodies form when rocky planets or large asteroids become hot enough to melt, allowing heavy metals to sink toward the center and lighter materials to float toward the surface. If such a body were subsequently shattered, the metallic core fragments could be ejected into interstellar space. This scenario would explain both the potential high density suggested by some mass estimates and the enhanced metallic signatures in the spectrum. Core fragments from differentiated bodies in our own solar system exist in the form of iron-nickel meteorites, which are composed almost entirely of metallic materials. An interstellar analogue of these objects would be fascinating from a scientific perspective, providing insights into planetary formation and evolution processes around other stars. The mass estimates for 3I Atlas remain highly uncertain, but they play a crucial role in constraining compositional models. The Hubble observations in July provided size constraints based on the brightness and extent of the coma, but translating these measurements into nucleus size requires assumptions about surface reflectivity and dust production efficiency. Different assumptions lead to size estimates ranging from a few hundred meters to several kilometers in diameter. When combined with estimates of the object's total mass based on its gravitational effects and orbital behavior, these size constraints yield density estimates that span more than an order of magnitude. If 3I Atlas is on the small and light end of the allowed range, its density would be consistent with typical comet nuclei, which are thought to be loosely bound mixtures of ice and rock with substantial porosity. If it falls toward the large and massive end of the range, its density would approach that of solid rock or even metallic materials. The uncertainty in these fundamental physical parameters creates space for speculation about exotic compositions, but it also demonstrates the limitations of remote sensing for characterizing small, distant objects. Even with the most sophisticated ground-based telescopes and space-based instruments, The basic question of whether 3I Atlas is primarily ice, rock, or metal remains unresolved based on observations available before the Mars window. The Mars-based observations during early October represented the best opportunity to resolve these compositional uncertainties. The improved viewing geometry and the potential for higher resolution measurements could have provided crucial constraints on nucleus size, mass, and spectroscopic properties. ESA's planned spectroscopic observations with the NOMAD instrument on the ExoMars Trace Gas Orbiter were specifically designed to search for trace gases and unusual molecular signatures that might reveal exotic compositions. The absence of real-time results from these Mars observations creates a significant gap in our understanding of 3I Atlas composition during the period when such data would have been most valuable. Composition can change as objects approach the Sun. The solar heating drives off volatile materials and exposes deeper layers of the nucleus. The Mars window coincided with a period of increasing solar heating that could have revealed compositional changes or exposed materials not visible during the earlier ground-based observations. Temperature-dependent processes play crucial roles in revealing comet composition. Different volatile materials sublimate at different temperatures, creating a sequence of compositional changes as objects approach the Sun. Water ice begins sublimating significantly when objects reach approximately 3 astronomical units from the Sun. Carbon dioxide becomes active at greater distances, while carbon monoxide can sublimate even in the cold outer solar system. Exotic volatiles like nitrogen or hydrogen would become active at even lower temperatures. The specific sequence and timing of volatile activation can provide important clues about nucleus composition and structure. Objects dominated by water ice show relatively little activity until they approach the inner solar system, then brighten rapidly as water sublimation increases. Objects rich in more volatile materials show activity at greater solar distances, but may not brighten as dramatically near perihelion if their most volatile components have already been depleted. The brightness evolution of 3I Atlas through its approach to perihelion will eventually provide important constraints on its volatile inventory and thermal properties. Objects with unusual compositions should show distinctive brightness patterns that differ from typical solar system comets. However, interpreting these patterns requires detailed models of nucleus structure, thermal properties, and gas production mechanisms that depend on having accurate measurements during critical phases of the object's approach. The potential for layered or heterogeneous composition adds another dimension to the analysis. Comet nuclei are thought to preserve materials from the earliest stages of planetary system formation, potentially including layers or regions with different compositions that formed under different conditions. If 3I Atlas represents material from the outer regions of its parent system, it might contain layers rich in different volatile species, creating complex patterns of gas production as solar heating penetrates to different depths. Alternatively, if the object experienced processing during its ejection from its parent system, or during its journey through interstellar space, its surface composition might differ significantly from its interior. Cosmic ray bombardment, interstellar dust erosion, and thermal cycling could have altered the surface layers while leaving the interior relatively unchanged. Such processing could create misleading spectroscopic signatures that don't accurately represent the bulk composition of the object. The resolution of these compositional mysteries depends on obtaining complete and accurate observational data from all phases of 3I Atlas's passage through our solar system. The Mars window provided unique opportunities for high-precision measurements during a critical phase of solar heating and volatile activation. The post-perihelion period will reveal how the object responds to maximum solar heating and whether its behavior matches predictions based on specific compositional models. The integration of all these observations will eventually provide the most complete picture possible of what this interstellar visitor is actually made of and what that composition reveals about conditions in its alien birthplace. Section 10. Classified assets and hidden observers. While civilian space agencies operate with varying degrees of transparency, A parallel universe of space surveillance exists within military and intelligence organizations. These classified assets possess capabilities that often exceed their civilian counterparts, operated by agencies whose primary mission is not scientific discovery but national security. Understanding this hidden infrastructure is crucial for evaluating whether the communications blackout during the Mars window concealed only administrative delays or something more significant. The United States Space Force, established in 2019 as the newest branch of the military, operates a comprehensive space surveillance network designed to track objects in Earth orbit and beyond. Their mission focuses primarily on cataloging satellites, monitoring space debris, and detecting potential threats to American space assets. However, the technical capabilities required for these missions overlap significantly with those needed to observe and characterize interstellar objects like 3IATIAS. The space surveillance network includes both ground-based and space-based sensors distributed globally. Ground-based radars like the Space Fence facility on Kwajalein Atoll can track objects thousands of kilometers away with remarkable precision. Optical telescopes operated by the Air Force Research Laboratory can detect and image satellites in geosynchronous orbit, approximately 36,000 kilometers from Earth. While these systems are optimized for tracking artificial objects in predictable orbits, their capabilities could theoretically be applied to natural objects passing through the solar system. The National Reconnaissance Office represents perhaps the most capable but least transparent component of America's space surveillance infrastructure. Established in 1961 but not officially acknowledged until 1992, the NRO designs, builds and operates reconnaissance satellites for intelligence gathering. Their capabilities are largely classified, but occasional glimpses suggest technological sophistication that rivals or exceeds the best civilian space telescopes. In 2012, the NRO donated 2 space telescopes to NASA that were described as having Hubble-class mirrors but designed for different missions. These telescopes, originally built for classified reconnaissance purposes, demonstrated that the intelligence community possesses optical systems comparable to the most advanced civilian instruments. If similar systems are currently operational and pointed at appropriate targets, they could potentially observe interstellar objects with resolution and sensitivity matching or exceeding civilian capabilities. The key difference between classified and civilian observations lies not in technical capability, but in data handling and release policies. Civilian observatories typically operate under scientific principles that favor data sharing, peer review, and open publication. Intelligence assets operate under classification systems that restrict access to observations based on national security considerations. Even observations of natural phenomena like comets could be classified if they reveal sensitive information about sensor capabilities, operational procedures, or surveillance priorities. The challenge for outside observers lies in detecting the activity of classified systems without access to their operational parameters or data products. However, certain indicators might suggest when these assets are being used for non-routine observations. Changes in satellite pointing patterns, modifications to ground station operations, or shifts in personnel assignments might indicate special observation campaigns, though such changes would likely be subtle and difficult to detect without inside information. Amateur radio operators and satellite trackers provide one potential source of independent information about classified space activities. These enthusiasts routinely monitor radio frequencies used by military satellites and can sometimes detect changes in communication patterns that indicate non-routine operations. If classified assets were conducting intensive observations of 3I Atlas during the Mars window, such activities might produce detectable changes in radio traffic patterns, though interpreting such signals would require considerable expertise and might not provide specific information about the nature of the observations. The international dimension of space surveillance adds complexity to any analysis of classified observations. Other nations operate their own military space surveillance systems with varying levels of capability and transparency. Russia's space surveillance network includes both Soviet-era facilities and modern systems, While China has been rapidly expanding its space monitoring capabilities in recent years, European nations contribute to both civilian and military space surveillance through organizations like the European Space Agency and NATO. This international network creates both opportunities and challenges for comprehensive observation campaigns. Multiple nations might independently observe the same interstellar object, providing cross-validation of unusual findings, but also complicating any attempts to coordinate information sharing or suppression. If 3I Atlas exhibited anomalous behavior during the Mars window, observations from multiple classified systems might exist, but coordinating the release or suppression of such information across different national intelligence organizations would be extremely difficult. The technological capabilities of modern military space surveillance systems are often underestimated by civilian observers. While specific technical parameters remain classified, publicly available information suggests systems capable of detecting objects much smaller and more distant than typically acknowledged. The ability to track space debris fragments a few centimeters in size at distances of thousands of kilometers implies sensitivity that could easily detect and characterize interstellar objects if properly configured and tasked. More sophisticated analysis capabilities might allow classified systems to extract information that civilian observers cannot obtain. Advanced signal processing, machine learning algorithms, and data fusion techniques developed for intelligence applications could potentially reveal subtle patterns or anomalies in interstellar object behavior that would be missed by conventional analysis methods. Such capabilities would be particularly valuable for detecting artificial signatures or unusual physical properties that might indicate non-natural origins. The temporal aspects of classified observations present another consideration. While civilian observatories typically schedule observations weeks or months in advance, military systems often maintain rapid response capabilities for emerging targets of interest. If initial observations of 3I Atlas revealed unexpected characteristics, classified systems might have been quickly retasked to conduct more intensive monitoring without the delays associated with civilian peer review and scheduling processes. The question of data retention and analysis timelines also differs significantly between civilian and classified systems. Civilian observatories typically process and release data according to scientific publication schedules that can extend over months or years. Classified systems might conduct real-time analysis and reach preliminary conclusions much more rapidly, but those conclusions would remain within intelligence channels rather than entering the public scientific record. The potential for compartmentalized observations within classified systems creates additional complexity. Different agencies or programs might conduct independent observations of the same object without necessarily sharing information with each other. This compartmentalization, designed to protect sensitive sources and methods, could result in multiple classified analyses of 3I Atlas that reach different conclusions or emphasize different aspects of the object's behavior. The legal and policy frameworks governing classified space observations also create barriers to information sharing even when no specific national security concerns are involved. Classification systems are designed to err on the side of caution, potentially restricting the release of information that might not actually harm security interests but could reveal operational capabilities or procedures. This conservative approach might prevent the release of 3I Atlas observations that would be scientifically valuable but are deemed too sensitive from an operational security perspective. The ultimate challenge for assessing the significance of classified observations lies in their fundamental inaccessibility to outside evaluation. Without access to the raw data, analysis methods, and institutional decision-making processes of classified systems, it's impossible to determine whether they observed anything unusual about 3I Atlas during the Mars window or any other period. The absence of public information from these sources cannot be interpreted as evidence either for or against anomalous findings. However, the existence of these capabilities and their potential application to interstellar object observations provides important context for understanding the complete picture of who was watching 3I Atlas during the critical Mars window. While civilian communications were suspended and international observers provided limited coverage, a substantial classified surveillance infrastructure remained operational and potentially active. Whether that infrastructure detected anything unusual, and whether such findings will ever reach the public domain, remains an open question that may never be definitively answered. Section 11. Information Control Mechanisms. The suppression of information during sensitive periods requires no grand conspiracy, no shadowy meetings, no dramatic orders from mysterious authorities. Modern governments have developed sophisticated, entirely legal mechanisms for controlling information flow that operate through established bureaucratic procedures and administrative regulations. Understanding these mechanisms is crucial for evaluating whether the silence during the Mars observation window resulted from routine administrative procedures or more deliberate information management. The foundation of information control in the United States rests on a complex legal framework that balances public access to government information with legitimate needs for security, privacy, and operational effectiveness. The Freedom of Information Act establishes the principle that government information should be publicly accessible, but it includes specific exemptions for national security information, law enforcement materials, trade secrets, and other categories deemed sensitive. These exemptions provide legal justification for withholding information without requiring explicit classification or censorship orders. The classification system represents the most formal mechanism for information control. Information can be classified as confidential, secret, or top secret, based on the potential damage its unauthorized disclosure might cause to national security. The classification process requires proper authority, documented justification, and periodic review for declassification. However, classification is often applied conservatively, with decision-makers erring on the side of protecting information rather than risking potential security breaches. For space-related information, classification decisions can be particularly complex. Observations of natural phenomena like comets typically wouldn't justify classification on their own merits, but the same observations might be classified if they reveal sensitive information about sensor capabilities, operational procedures, or surveillance priorities. This creates situations where scientifically mundane observations might be legally restricted because of how they were obtained rather than what they contain. The compartmentalization of information within government agencies creates additional barriers to public access, even when formal classification isn't involved. Different offices and programs operate under different authorities, funding sources, and operational requirements. Information that crosses these boundaries must navigate complex approval processes that can delay or prevent public release, even when no security considerations are involved. During government shutdowns, these normal information control mechanisms are supplemented by emergency procedures that suspend most public-facing activities. The Anti-Deficiency Act prohibits federal employees from obligating resources that haven't been appropriated by Congress, which effectively shuts down most non-essential government communications. Public affairs offices are closed, websites stop updating, and press releases cease not because information is being deliberately suppressed, but because the people responsible for public communication are legally prohibited from working. This creates a perfect legal framework for information control that requires no special orders or explicit censorship. The mechanisms for restricting public access to government information are automatically activated by political failure to pass appropriations bills. Any information that would normally be shared with the public simply accumulates in digital storage systems, waiting for funding to be restored so that people can be paid to process and release it. The timing precision of these mechanisms is particularly significant for understanding the Mars window communications blackout. Government shutdowns typically result from extended political negotiations with deadlines that can be predicted, but are rarely precise to the hour. The October 1st midnight deadline was fixed by law, but political agreements often emerge at the last minute, sometimes preventing shutdowns or limiting them to brief periods. The fact that this particular shutdown began precisely when 3I Atlas entered its optimal observation window at Mars suggests either extraordinary coincidence or careful timing by parties who understood the astronomical significance of early October 2025. The orbital mechanics that determined the Mars window had been calculated and published months in advance, making the timing of optimal observations predictable to anyone with access to astronomical planning documents. International comparisons highlight the effectiveness of these American information control mechanisms. The European Space Agency continued normal operations throughout the October period, maintaining public communications about their Mars observation plans and providing updates about preliminary results. This transparency created a stark contrast with American silence that made the shutdown-induced information gap more noticeable and potentially more suspicious than it might have been in isolation. The post-shutdown information release patterns provide important clues about whether routine administrative delays or more deliberate information management explains the communications gap. Normal shutdown procedures predict that accumulated information should be released in batches once funding is restored and personnel return to work. Delays beyond this normal processing time might indicate additional review procedures or sensitivity concerns that extend beyond routine administrative backlogs. The structure of government information systems also affects how information can be controlled or released. Modern digital systems create detailed logs of when information is created, modified, accessed, and transmitted. These metadata records can reveal patterns of unusual activity or special handling that might indicate sensitivity beyond routine classification or administrative procedures. However, accessing these logs requires insider knowledge or formal investigative procedures that are not readily available to outside observers. Private contractors play an increasingly important role in government space operations, creating additional complexity in information control mechanisms. Many space missions involve significant participation by private companies that operate under different legal frameworks than government agencies. Information generated by contractors might be subject to proprietary restrictions or contractual confidentiality agreements that prevent public release even when no security classification is involved. The international dimension of modern space operations creates additional challenges for comprehensive information control. When multiple nations contribute to observation campaigns or data analysis, coordinating information release policies becomes extremely difficult. Even if American agencies choose to restrict information sharing, data from international partners might reveal similar findings through independent channels that are not subject to American administrative procedures. The technical complexity of modern space observations also affects information control possibilities. Raw observational data requires significant processing and analysis before it can be meaningfully interpreted. This processing phase provides opportunities for selective emphasis, data filtering, or analytical choices that can affect the conclusions reached without requiring explicit modification of the underlying observations. Such technical manipulation would be difficult to detect without access to the complete raw datasets and detailed knowledge of the processing procedures used. The peer review process in scientific research provides another mechanism that can affect information flow, though typically in the direction of increased scrutiny rather than suppression. Preliminary findings must survive review by independent experts before publication in scientific journals. This process can delay the release of results by months or years, but it typically ensures that published findings meet rigorous standards of evidence and analysis. However, the peer review system can also be influenced by institutional pressures or policy considerations that affect which results receive priority for publication and which encounter additional scrutiny or delay. Controversial findings or results with potential policy implications might face more intensive review processes that could delay their appearance in the public scientific literature, even when the underlying data is sound. The interaction between these various information control mechanisms creates a complex environment where information can be restricted, delayed, or filtered through multiple overlapping processes. Understanding this environment is crucial for evaluating claims about information suppression and for developing realistic expectations about when and how sensitive observations might eventually reach the public domain. The ultimate test of information control mechanisms lies in their consistency and proportionality. If observations of 3I Atlas during the Mars window were subject only to routine administrative delays caused by the government shutdown, the eventual data releases should be complete, well documented, and consistent with independent observations from other sources. If additional information control mechanisms were involved, the data releases might show gaps, inconsistencies, or processing artifacts that indicate special handling or selective release procedures. Section 12. Alternative Hypothesis Matrix. Scientific investigation requires systematic evaluation of competing explanations, each tested against available evidence, and assigned credibility based on how well it accounts for observed phenomena. For the events surrounding 3I Atlas during the Mars observation window, multiple hypotheses exist that range from mundane bureaucratic coincidence to exotic possibilities involving artificial objects or covert operations. Evaluating these hypotheses objectively requires understanding their predictions, their evidence requirements, and their falsification criteria. Hypothesis 1. Bureaucratic coincidence. This represents the null hypothesis, the simplest explanation that requires the fewest assumptions. According to this interpretation, the government shutdown that began on October 1, 2025, was the result of routine political dysfunction, with timing that coincidentally aligned with 3I Atlas's Mars observation window. NASA's communications blackout resulted from legal requirements under the Anti-Deficiency Act, not from any desire to conceal observations. Scientific data was collected normally by Mars-based instruments, but the processing and public release of this data was delayed by administrative disruptions. The evidence supporting this hypothesis includes NASA's publicly available Continuity of Operations Plan, which explicitly states that public communications will cease during funding lapses. Historical precedent shows that government shutdowns routinely delay scientific data releases without indicating suppression of sensitive findings. The duration of the shutdown, 7 days, matches the timeline needed for congressional negotiations rather than the astronomical significance of the Mars window. This hypothesis predicts that complete observational data from the Mars window will eventually be released through normal scientific channels. The data should show 3I Atlas behaving like a conventional comet, with brightness variations, spectroscopic signatures, and orbital perturbations consistent with natural outgassing processes. International observations from ESA and other sources should corroborate these findings, showing consistent results across independent measurement systems. Falsification criteria for this hypothesis include significant discrepancies between NASA and international observations, unexplained gaps in data coverage during the Mars window, or evidence of artificial signals or anomalous behavior that require exotic explanations. The discovery of classification orders or special handling procedures for 3I Atlas data would also weaken this hypothesis. Hypothesis 2. Natural but unusual object. This hypothesis accepts that 3I Atlas is a natural object from another star system, but suggests it possesses characteristics that make it scientifically exceptional. The object might be a fragment of a differentiated body with unusually high metal content, an exotic comet composed of materials rare in our solar system, or a pristine sample of interstellar material that preserves chemical signatures from its birthplace around another star. Supporting evidence includes preliminary spectroscopic detections of enhanced nickel emission, mass estimates that suggest higher density than typical comets, and the general rarity of interstellar objects that makes each visitor potentially unique. The scientific value of such an object would justify intensive observation campaigns and careful analysis procedures that might delay public data releases beyond normal timelines. This hypothesis predicts that detailed analysis will reveal compositional or structural characteristics that distinguish 3I Atlas from previously observed interstellar objects and from typical solar system comets. the orbital behavior should remain consistent with natural gravitational and outgassing forces, but the specific pattern of volatile release might reflect unusual nuclear composition or structure. Falsification would occur if comprehensive analysis reveals composition and behavior indistinguishable from conventional comets, if claims of unusual characteristics prove to result from observational errors or misinterpretation, or if artificial signatures are detected that indicate technological rather than natural origins. Hypothesis 3. Artificial object. This represents the most exotic hypothesis, suggesting that 3I-ETLS is not a natural comet, but an artificial object of extraterrestrial origin. This could range from an active probe conducting reconnaissance of our solar system to derelict technological debris from an advanced civilization. Such an object might exhibit characteristics that mimic natural comet behavior, while containing technological components or artificial signals. Current evidence for this hypothesis is extremely weak, consisting primarily of speculation based on the anomalous behavior of Oumuamua and the enhanced public interest in potential extraterrestrial technology. Claims of unusual orbital perturbations, artificial signals, or structured morphology remain unverified and largely speculative. This hypothesis predicts the detection of coherent electromagnetic signals, orbital maneuvers that cannot be explained by natural forces, spectroscopic signatures of refined or processed materials, or morphological features that suggest artificial construction. The object's behavior should show evidence of active control or technological function rather than passive response to solar heating. Falsification requires demonstrating that all observed characteristics of 3I-Atlas can be explained by natural processes, that no artificial signals are detectable despite competent searches, and that claims of anomalous behavior result from observational errors or misinterpretation rather than genuine technological activity. Hypothesis 4. Covert observation campaign. This hypothesis suggests that the significance of 3I-Atlas was recognized by intelligence or military organizations, leading to classified observation campaigns that operated parallel to civilian scientific activities. The government shutdown provided convenient cover for intensive observations that might have revealed sensitive information about surveillance capabilities or strategic interests in space-based phenomena. Evidence for this hypothesis is largely circumstantial, based on the existence of classified space surveillance systems with capabilities that could observe interstellar objects, and the convenient timing of the communications blackout during their optimal observation window. Historical precedent exists for military interest in astronomical phenomena that might affect space operations or reveal information about extraterrestrial activity. This hypothesis predicts that complete scientific data from the Mars window may never be publicly released, or may be released only after extensive delays and possible redaction of sensitive information. Independent observations from international sources might reveal discrepancies with American data releases if classified observations detected phenomena that civilian instruments missed or misinterpreted. Falsification would occur if complete scientific data is released promptly after administrative delays end, if the data is fully consistent with international observations, or if leaked information reveals that no special observation campaigns were authorized or conducted during the Mars window. Hypothesis 5. Information management. This hypothesis suggests that the timing of the government shutdown was not entirely coincidental, but resulted from recognition that 3I-Atlas observations might produce results that required careful analysis and controlled release. Rather than explicit suppression, this would involve using existing administrative procedures to create time for thorough evaluation of potentially sensitive findings. Evidence for this hypothesis would include unusually precise timing of the shutdown relative to the Mars observation window, evidence of advanced planning for post-shutdown information handling, or patterns in data release that suggest selective emphasis or de-emphasis of particular findings. The hypothesis requires coordination between political and scientific leadership that might be difficult to detect or verify. This hypothesis predicts that data releases will eventually occur but may show evidence of careful curation, selective emphasis, or coordinated messaging that goes beyond normal scientific communication practices. The timing and completeness of releases might reflect policy considerations rather than purely scientific priorities. Falsification would occur if data releases show no evidence of special handling, if the timing of the shutdown can be completely explained by documented political factors unrelated to astronomical observations, or if leaked information reveals no coordination between administrative and scientific decision-making processes. Evaluation framework. These hypotheses can be ranked based on their consistency with known facts, the number of assumptions they require, and their predictive power for future observations. The bureaucratic coincidence hypothesis ranks highest due to its consistency with documented administrative procedures and its requirement for fewer unverified assumptions. The natural but unusual object hypothesis ranks second, as it requires only that 3I Atlas possess characteristics that distinguish it from typical comets, which is scientifically plausible. The remaining hypotheses require increasingly speculative assumptions about hidden capabilities, coordinated deception, or exotic phenomena that lack strong evidential support. However, all hypotheses can be tested against future data releases and observations, providing objective criteria for evaluating their validity as more information becomes available. The strength of this framework lies in its systematic approach to evaluating competing explanations and its explicit criteria for falsification. Rather than selecting preferred explanations based on dramatic appeal or political considerations, this approach allows evidence to determine which hypotheses survive critical scrutiny and which must be abandoned as inconsistent with observed reality. Section 13. The Signal Search Protocol. The possibility that 3I Atlas might be transmitting artificial signals represents one of the most extraordinary claims requiring extraordinary evidence. While the scientific community remains skeptical of technological interpretations for interstellar objects, the question deserves systematic investigation using rigorous methods developed by the Search for Extraterrestrial Intelligence community. Understanding what such signals might look like, how they could be detected, and what would constitute convincing evidence provides crucial context for evaluating any claims about artificial transmissions from this object. Artificial signals from a technological source would exhibit characteristics that distinguish them from natural astrophysical phenomena. Natural objects emit broadband radiation across wide ranges of frequencies, with spectral distributions determined by temperature, chemical composition, and physical processes like thermal emission or synchrotron radiation. Technological signals, in contrast, typically concentrate energy in narrow frequency bands to maximize transmission efficiency and minimize interference with other communications. The technical specifications for detecting signals from 3I Atlas depend on the object's distance, velocity, and the sensitivity of available radio telescopes. During the Mars observation window in early October, the object was approximately 30 million kilometers from Earth, moving at roughly 25 kilometers per second relative to our planet. These parameters create specific requirements for signal detection that can be calculated precisely. The inverse square law governs how signal strength decreases with distance. A transmitter that would produce a detectable signal at close range becomes extremely faint when moved to interstellar distances. For comparison, the most powerful radio transmitters on Earth would be barely detectable at 30 million kilometers using our most sensitive radio telescopes. Any signal from 3I Atlas would need to be either extremely powerful or highly directional to be detectable from Earth. The object's velocity creates additional detection challenges through Doppler shifting. As 3I Atlas moves relative to Earth, any transmitted signal will be shifted in frequency by an amount proportional to the relative velocity. This shift changes continuously as the object's trajectory curves through our solar system, creating a time-varying frequency drift that must be accounted for in search algorithms. Modern SETI search techniques have developed sophisticated methods for detecting drifting signals that account for these Doppler effects. Software can search for signals across wide frequency ranges while tracking the expected drift rate based on the object's known trajectory. This capability makes it theoretically possible to detect signals from moving sources like 3I Atlas, but it requires precise knowledge of the object's position and velocity vectors. The frequency selection for searches involves balancing technical constraints with theoretical predictions about optimal communication frequencies. The waterhole between hydrogen and hydroxyl emission lines at 1.4 to 1.7 GHz has long been considered a natural choice for interstellar communication because these frequencies experience minimal interference from natural sources. However, technological civilizations might choose other frequencies based on their technical capabilities or communication requirements. The duration and timing of observations create additional strategic considerations for signal searches. Continuous monitoring would be ideal, but is rarely practical with large radio telescopes that have many competing demands for observation time. The Mars observation window represented a particularly favorable period for signal searches, because the object was at relatively close range and moving slowly enough for extended tracking. Several major radio astronomy facilities possess the sensitivity and technical capabilities needed for searching for signals from 3I Atlas. The Arecibo Observatory, before its collapse in 2020, would have been ideal for such searches. The Very Large Array in New Mexico, the Green Bank Telescope in West Virginia, and the FAST telescope in China all have sufficient sensitivity for detecting powerful signals from the object's distance during the Mars window. International coordination of search efforts would significantly improve the chances of detection while providing crucial verification of any claimed signals. Multiple independent observations of the same signal would be essential for establishing credibility, as radio frequency interference from terrestrial sources creates numerous false positives in SETI searches. A signal detected by multiple facilities using different equipment and analysis methods would be far more convincing than isolated claims from single observations. The technical characteristics of any detected signal would provide important clues about its nature and origin. Bandwidth, modulation patterns, power levels, and frequency stability all carry information about the transmitting system. Natural astrophysical sources typically produce broadband noise or emission lines with characteristic spectral signatures. Technological sources might show evidence of modulation, error correction, or other information encoding techniques. The search for optical signals provides another avenue for detecting artificial transmissions. Powerful laser pulses or continuous laser beams could potentially be detected using optical telescopes equipped with high-speed photometers. Optical SETI searches look for brief flashes or continuous signals that stand out against the background starlight, using techniques similar to those developed for detecting pulsars or other rapidly varying astronomical sources. The timing of any detected signals relative to the object's trajectory would provide crucial information about their origin. Signals that appear only when telescopes are pointed at 3I Atlas, that show Doppler shifts consistent with the object's motion, and that disappear when the object moves out of the telescope's field of view would strongly suggest origin from the object itself rather than terrestrial interference or background astronomical sources. However, the absence of detected signals cannot be interpreted as proof that no artificial transmissions exist. The sensitivity limits of current radio telescopes, the limited time available for observations, and the vast range of possible frequencies and signal types create numerous opportunities for missing real signals. A negative result from signal searches would constrain the power and frequency range of any potential transmissions, but wouldn't definitively rule out technological activity. The analysis and verification of any claimed signal detections would require extensive technical analysis and independent confirmation. Radio frequency interference from satellites, ground-based transmitters, and electronic equipment creates a constant background of artificial signals that can mimic extraterrestrial transmissions. Distinguishing genuine signals from interference requires careful analysis of propagation characteristics, frequency stability, and correlation with known terrestrial sources. The scientific community has established protocols for handling potential SETI detections that emphasize verification, international cooperation, and careful public communication. Any credible signal detection would trigger intensive follow-up observations using multiple facilities and analysis techniques. The results would be shared with the international astronomical community for independent verification before any public announcements. The political and social implications of confirmed signal detection from an interstellar object would be enormous, potentially affecting everything from space policy to international relations. The scientific protocols for handling such discoveries emphasize measured response and careful verification precisely because of these broader implications. False alarms could damage public trust in scientific institutions and create unnecessary political tensions. The current status of signal searches for 3I Atlas remains unclear due to the limited public information about observation campaigns during the Mars window. While several radio astronomy facilities have the technical capability to conduct such searches, most SETI observations are conducted by dedicated research programs rather than routine astronomical surveys. Whether any systematic signal searches were conducted during the optimal observation period in early October remains to be documented in the public scientific literature. The post-conjunction period, when 3I Atlas emerges from behind the Sun in late November and December, will provide additional opportunities for signal searches as the object remains visible from Earth-based telescopes. These later observations will be crucial for verifying or refuting any claims about artificial signals detected during the Mars window, and for conducting systematic searches that can provide definitive constraints on the object's potential technological activity. Section 14. Community Investigation Framework. The democratization of space science observation means that important questions about 3I Atlas need not remain solely in the hands of government agencies or professional astronomers. Amateur astronomers, citizen scientists, and independent researchers possess tools and capabilities that would have been unimaginable just decades ago. Creating a systematic framework for community investigation ensures that the search for truth about this interstellar visitor remains open, collaborative, and resistant to any attempts at information suppression or selective interpretation. The foundation of effective community investigation rests on understanding what data should exist and where to find it. Government space missions generate predictable digital footprints that persist across multiple archives and backup systems. Spacecraft telemetry logs, instrument command sequences, and observation schedules create paper trails that are difficult to suppress completely. Understanding these data sources provides roadmaps for independent verification of official claims about what was or wasn't observed during the Mars window. NASA's Planetary Data System represents the primary archive for American space science data, with standardized formats and search capabilities that allow detailed investigation of mission activities. While data releases may be delayed during shutdowns or for scientific analysis, the archive structure itself provides clues about what observations were planned or attempted. Missing data files, unusual gaps in temporal coverage, or inconsistent metadata can reveal whether normal procedures were followed during sensitive periods. The European Space Agency maintains parallel archives for Mars Express and ExoMars Trace Gas Orbiter data, typically with more rapid release schedules than American missions. These European datasets provide crucial cross-references for evaluating the completeness and accuracy of NASA data releases. Discrepancies between simultaneous observations of the same object by different agencies would indicate either technical problems or deliberate differences in data processing and release policies. Amateur astronomical networks provide independent observation capabilities that operate outside government control and institutional constraints. Dedicated amateur astronomers have contributed significant observations to 3I Atlas tracking since its discovery, using sophisticated equipment that can rival professional facilities for certain types of measurements. These independent observations provide baselines for evaluating claims about anomalous behavior during periods when official observations might be unavailable or suspect. The The Minor Planet Center's database of observations provides a comprehensive record of all reported measurements of 3I Atlas from discovery through the present. This database includes contributions from professional observatories, amateur astronomers, and automated survey systems worldwide. Analyzing patterns in this observational record can reveal gaps, inconsistencies, or anomalies that might indicate missing or suppressed data from particular time periods or geographic locations. Radio monitoring of spacecraft communications provides another avenue for independent verification of mission activities. Amateur radio operators routinely monitor the frequencies used by Mars orbiters to communicate with Earth, tracking data transmission schedules and communication patterns. Unusual activity during the Mars observation window, such as extended high data rate transmissions or communications outside normal schedules, might indicate intensive observation campaigns that weren't publicly acknowledged. Social media monitoring and web archiving services preserve records of official communications and their timing that can be analyzed for patterns, suggesting special handling of sensitive information. The Wayback Machine and similar services capture historical versions of mission websites, press releases, and social media posts. Changes in communication patterns, deleted content, or unusual delays in posting routine updates can provide clues about institutional responses to potentially sensitive observations. Metadata analysis of released images and data files provides technical tools for detecting evidence of post-processing, editing, or selective release procedures. Digital images contain extensive header information about instrument settings, processing parameters, and timing that can reveal whether normal procedures were followed. Inconsistencies in metadata, unusual processing artifacts, or statistical anomalies in file characteristics might indicate special handling that goes beyond routine scientific analysis. Crowdsourced analysis projects can leverage the distributed intelligence of large groups to identify patterns or anomalies that might be missed by individual researchers. Projects like Galaxy Zoo have demonstrated the effectiveness of citizen science approaches for analyzing large astronomical datasets. Similar approaches could be applied to 3I Atlas observations, with volunteers searching for unusual features, inconsistencies, or gaps in the data record. International coordination of community investigation efforts ensures that information suppression in one country cannot prevent independent analysis by researchers in other nations. The global nature of astronomy and the international character of many space missions create multiple channels for information flow that are difficult to control comprehensively. Researchers in different countries can compare notes, share data, and coordinate analysis efforts to build comprehensive pictures that resist national information management policies. Technical training and resource sharing enable community investigators to develop the specialized skills needed for sophisticated data analysis. Understanding astronomical data formats, image processing techniques, and statistical analysis methods requires education and practice, but online resources and collaborative learning opportunities make these skills increasingly accessible to motivated amateur researchers. Verification protocols ensure that community investigation maintains scientific rigor and avoids the speculation and misinformation that can undermine credible research. Establishing standards for evidence quality, requiring independent confirmation of significant findings, and maintaining clear distinctions between verified facts and provisional hypotheses help preserve the scientific integrity of community research efforts. Legal frameworks for accessing government information provide formal channels for obtaining data that might not be released through normal scientific procedures. Freedom of Information Act requests, congressional oversight mechanisms, and international data sharing agreements create multiple avenues for accessing information that might be withheld for administrative or policy reasons rather than legitimate security concerns. Documentation and preservation of community investigation results ensures that important findings survive attempts at suppression or institutional forgetting. Distributed archives, multiple backup systems, and international hosting of sensitive data help preserve important information that might be vulnerable to deletion or modification, by organizations with interests in controlling the narrative around 3IATLS. The ultimate goal of community investigation is not to replace professional scientific research, but to provide independent verification and alternative perspectives that strengthen the overall search for truth. Professional astronomers have access to sophisticated instruments and deep technical expertise, but they also operate within institutional constraints that can affect their ability to pursue controversial questions or challenge official interpretations of sensitive observations. Community investigation provides checks and balances that help ensure scientific integrity remains paramount regardless of political pressures or institutional interests. When government agencies are silent, when professional institutions are constrained, when international cooperation is limited, the distributed capabilities of the global amateur astronomy community provide resilient alternatives for pursuing important questions about our place in the universe. The framework for investigating 3IATL serves as a model for future situations where conventional channels of scientific communication might be compromised or constrained. As space exploration becomes increasingly commercialized and militarized, maintaining independent capabilities for investigation and verification becomes crucial for preserving public access to important discoveries about our cosmic environment. The tools, techniques, and organizational approaches developed for investigating this interstellar visitor will remain valuable long after 3I/Atlas fades into the cosmic background. The next unusual object, the next convenient shutdown, the next suspicious timing of information gaps will find a community better prepared to ask hard questions, demand complete answers, and pursue truth regardless of institutional preferences for convenient silence. Section 15. The Post-Conjunction Revelation. The cosmic clockwork that governs 3I/Atlas's journey through our solar system provides one final opportunity for resolution. As this interstellar visitor emerges from behind the Sun in late November and December 2025, it carries with it the evidence needed to validate or refute every hypothesis proposed about its nature and the circumstances surrounding its Mars encounter. This post-conjunction reappearance represents more than just another observation opportunity. It represents a reckoning with the questions raised during those 7 silent days in October. The physics of solar conjunction creates a natural pause in the 3I/Atlas story that serves multiple functions. From Earth's perspective, the object becomes unobservable when it passes too close to the Sun's position in our sky. This conjunction period, lasting several weeks, provides time for data analysis, peer review, and institutional decision-making about how to present whatever was observed during the Mars window. When 3I/Atlas reappears, it will be as if the cosmic curtain has been raised on the final act of this interstellar drama. The observational capabilities available during the post-conjunction period differ significantly from those that existed during the Mars window. Ground-based telescopes will once again have clear views of the object, free from the solar glare that complicated observations in early October. The world's most powerful observatories can be trained on 3I/Atlas, providing independent verification of any characteristics claimed based on Mars-based observations. The Hubble Space Telescope and James Webb Space Telescope represent the pinnacle of space-based observation technology, with capabilities that exceed even the most sophisticated Mars orbiters for detailed spectroscopy and high-resolution imaging. These premier facilities can be scheduled for target of opportunity observations that provide definitive measurements of 3I/Atlas's composition, structure, and behavior. The data they collect will serve as the gold standard for evaluating all previous claims about the object's nature. International collaboration during the post-conjunction period provides crucial cross-checks for any controversial findings from the Mars window. Observatories in multiple countries, operating under different institutional frameworks and political constraints, can conduct independent observations of the same object during the same time periods. This distributed observation network makes comprehensive information suppression extremely difficult and provides multiple perspectives on any unusual characteristics the object might exhibit. The temporal evolution of 3I Atlas's properties as it recedes from perihelion offers insights into its internal structure and composition that couldn't be obtained from single-epoch observations. Comets typically show characteristic changes in brightness, gas production rates, and spectroscopic signatures as solar heating penetrates different depths into their nuclei. These evolutionary patterns provide fingerprints that can distinguish between different compositional models and reveal whether the object behaves like conventional comets or exhibits anomalous characteristics. The orbital mechanics of the post-conjunction period provide the ultimate test of whether 3I Atlas experienced any anomalous forces or perturbations during its passage through the inner solar system. The Minor Planet Center's orbital solutions, updated with months of additional observations, will reveal whether the object's trajectory can be explained entirely by gravitational forces and normal comet outgassing, or whether unexplained accelerations require more exotic explanations. The cadence and completeness of official data releases during the post-conjunction period will provide important clues about whether the Mars window silence concealed routine observations or something more significant. Normal scientific procedures predict specific timelines for data processing, analysis, and publication. Delays beyond these normal procedures, gaps in data coverage, or inconsistencies with international observations might indicate special handling that goes beyond routine administrative delays. The amateur astronomy community's response to 3I Atlas's reappearance will provide independent verification of professional observations and claims. Skilled amateur astronomers possess equipment capable of detecting brightness variations, spectroscopic features, and orbital anomalies that would confirm or refute official characterizations of the object. This distributed observational network operates outside institutional constraints and provides resilient verification capabilities. Radio astronomy facilities worldwide will have opportunities to conduct systematic searches for artificial signals during the post-conjunction period. Unlike the Mars window, when such searches might have been conducted by classified systems without public documentation, the reappearance period allows open, international collaboration on signal detection efforts. The results of these searches will provide definitive constraints on any technological activity associated with 3I Atlas. The scientific community's treatment of 3I Atlas during the reappearance period will reveal institutional attitudes toward controversial or potentially sensitive observations. Peer review processes, journal publication decisions, and conference presentation opportunities all provide indicators of whether the scientific establishment treats this object as routine or recognizes unusual characteristics that merit special attention. Media coverage and public communication during the post-conjunction period will demonstrate whether transparency concerns raised during the Mars window have been addressed, or whether information management continues to shape public understanding of this interstellar visitor. The contrast between official communications and independent analysis will reveal the completeness and honesty of institutional disclosure about 3I Atlas observations. The integration of Mars window data with post-conjunction observations will provide the most comprehensive test of the various hypotheses proposed to explain the events of early October 2025. If the Mars observations were routine and complete, they should mesh seamlessly with later data to create a coherent picture of 3I Atlas's behavior throughout its solar system passage. Discontinuities, inconsistencies, or gaps in this integrated picture would indicate problems with the official narrative. The long-term implications of the 3I Atlas investigation extend far beyond this single interstellar object. The methods developed for community investigation, the precedents established for information transparency, and the institutional responses to public scrutiny will all influence how future discoveries are handled. As interstellar objects become more common due to improved detection capabilities, the frameworks developed for investigating 3I Atlas will serve as templates for maintaining scientific integrity and public access to important discoveries. The ultimate resolution of questions raised during the Mars window depends not just on new observations, but on the institutional will to provide complete and honest accounting of what was observed during those 7 silent days. The post-conjunction period provides opportunities for verification and cross-checking that can expose any discrepancies between official claims and observational reality. Whether institutions take advantage of these opportunities to demonstrate transparency or continue patterns of selective disclosure will determine public trust in their handling of potentially sensitive discoveries. The promise implicit in this investigation is accountability through evidence. Claims made during the information blackout can be tested against independent observations. Hypotheses proposed to explain anomalous behavior can be validated or falsified through systematic investigation. The democratic tools of science, when properly applied, provide mechanisms for distinguishing truth from speculation, regardless of institutional preferences or political constraints. As 3i Atlas fades into the cosmic background, carrying with it the secrets of its alien birthplace, the questions raised about its passage through our solar system will remain as permanent additions to our understanding of how science, politics, and public communication intersect during moments of potential discovery. The next interstellar visitor will find a community better prepared to ask hard questions, demand complete answers, and ensure that the search for cosmic truth remains open to all humanity rather than confined to the closed channels of institutional secrecy. The lights have come back on, the data is flowing again. The post-conjunction observations are beginning. Now we discover whether the silence of October 2025 concealed a bureaucratic coincidence or something far more significant. The universe doesn't keep its secrets forever, but it requires persistent, intelligent, and courageous questioning to reveal them. That questioning continues, carried forward by everyone who refuses to accept convenient explanations when extraordinary possibilities demand extraordinary investigation. The final chapter of the 3i Atlas story has yet to be written, but the framework for writing it honestly and completely now exists. Whether institutions choose to use that framework or continue patterns of selective disclosure will determine not just our understanding of this particular cosmic visitor, but our preparedness for the greater discoveries that await in the vast, mysterious expanse between the stars.